Right. Well, thank you all for joining us. I'm Caroline Taylor, Director of Research and Development here at EarthShift Global. Thank you all for joining us for the final webinar of our fall season. We will, a couple bookkeeping notes before we get started. This is being recorded and it will be made available shortly after the webinar. And questions I will ask, so please go ahead and send them to me by chat directly. You'll see on the bottom of the screen a little chat icon. If you'll send them to me, I'll ask them. And we will hold questions until the end and ask them then. So I'm really pleased to introduce today's speakers. We have Casey Morris and Bill Bernstein, both from NIST. And Casey is the vice chair of the ASTM team working on sustainable manufacturing and leads the information and modeling and testing group in NIST's engineering lab. Bill is on the ISO working group for their standards on engineering and evaluating environmentally relevant manufacturing factors. He's part of the life cycle engineering group in this engineering lab. So we have a couple of real experts today who are going to talk to us about sustainable manufacturing standards and how they're developing and evolving. So Casey and Bill, I'll hand it off to you. Thank you so much.
Thank you. Hi. Here's our contact information. If anybody wants to reach out to us after the talk today, we're happy to hear from you. And with that said, let's go into next slide. Sorry, Bill's helping me with the controls. Okay, so I'm going to talk to you a little bit about the work that's being done currently within both ASTM and ISO working groups on standards for sustainable manufacturing specifically. And we'll just start out with a little bit of context setting for what that means as far as manufacturing standards, what that scope is. So first of all, I just want to start out with, you know, there's been a lot of definitions for what sustainability itself is, and it varies a lot. But the bottom line in all of it is that everybody's going to need to do their part to create a sustainable future. And so we are very much focused here at NIST in the engineering lab on manufacturers and what manufacturers can do in terms of performance improvements more generally and understanding their performance and more specifically in this area of sustainability. Sorry. Okay, so just a quick review of where, as a society, we've kind of come with understanding sustainability and environmental impact. And so early on, like in the 70s, when you know, our population was starting to get very large and we were kind of using resources very freely, there became an awareness that we needed to have more control over that. And so there was a lot of pollution prevention activity and testing of pollution controls. But as time went on, people got a little more sophisticated to start to understand how we can control the environmental impacts more broadly, looking at things from beyond pollution prevention to environmental management and product stewardship, how to design things for the environment, design things for the life cycle. And then finally, we're kind of in a stage now where more transparency is being demanded so that people are able to report actually what their environmental impacts are. So what is the manufacturer's role in all of this? So if you look at a product life cycle, which this figure here shows, is you start with product design, go into raw material extraction, into manufacturing, and then look at the distribution, the retailing, and the disposal of the products and reuse. The work that we do is primarily focused in this little shape here that really is centered on manufacturing and how manufacturers use the materials they get and how they consume those materials and how they impact the environment. So if you look at the impact that manufacturing has on the environment, the good well, good or bad, one thing you will see is that there's a strong correlation between cost and environmental impact. So that is a good motivator for manufacturers to try and address their sustainability impact beyond just being good citizens of the world. In the U.S., the environmental impact from manufacturing is about a third of the total energy use. And so in discrete manufacturing, which we focus in a little more closely, is about 8%. But it's a fairly large portion of our impact on the environment. So sustainability is good for business, for manufacturers. In some ways, it's business as usual, because manufacturers are always trying to figure out how to be more efficient and use the resources more efficiently. But it's also good for them socially to integrate concerns about workers and the consumers into their business practices, and of course economically to be able to identify what the return on investment of better practices are. That creates more motivation for them. So just to recap, sustainability is important for our society. For the manufacturing industry, it's actually very integral as well. And early efforts to address sustainability really focused on regulation and understanding impacts, but now we can go much more deeply in understanding what those impacts are and trying to understand what the trade-offs will be of implementing those impacts. And so that's the standards that we've been working on are more in that area of trying to understand trade-offs. So I think this is where, oops. Okay, Bill and I are coordinating this talk a little bit, and I missed my cue there. But okay, so anyway, so a lot of manufacturers, small, medium-sized, large manufacturers, they are facing increasing pressures to be more sustainable and to demonstrate that they're being more sustainable. A lot of them have implemented environmental management systems. They've completed energy audits. They've put recycling programs in place. They've changed out their light bulbs. They've kind of done the low-hanging fruit of improving their environmental impact. But we know there's a lot more that can be done, but that's going to be a more difficult problem for them to address. And so they are looking at, it's time that they start looking more closely at what their processes are and how they can save energy and materials in looking closely at those. And so at the same time, we have this new movement coming along, or phenomenon coming along, of digital manufacturing in the industrial Internet of Things, being able to collect data everywhere, being able to put sensors wherever you want and collect a lot of data and use that data to drive decisions. And so we think that's going to be very fundamental to creating more efficiency for the manufacturers. And so just to give you a little bit of an idea of manufacturing, the types of energy used in manufacturing, a lot of that is devoted to thermal processes, which right now are really not being closely monitored. And with this new technology coming along, there's a big opportunity to do close monitoring of that and in situ control so that these processes can be made much more efficient. So that's one area where there's going to be a lot of reduction in energy use. But all across the supply chain, well, all across the enterprise, from the device and machine levels up through the supply chain, there's a lot of opportunities to create more efficiencies along those dimensions as well. And then there's also opportunities looking at the whole product design process, because ultimately people are familiar with things such as life cycle analysis. You have environmental impacts that you want to reduce, and when it comes to product design, when you start the design, it's very much a forward-thinking process. You have things that you want to accomplish, functions you want to accomplish, and you have to, each step along the way, make decisions that are going to support those functions. You have to figure out what components you want in your products, what types of materials you're going to use, how those products will be manufactured, what processes and how those processes interact with the materials. And geometry comes into play there. What are the shapes you're trying to produce? And that will interact differently with the manufacturing process and materials. And the combination of those things create different types of environmental impacts. And then also looking at the performance of the final product, How reliable does it need to be? What's its life expectancy? Those are all decisions that a designer needs to make along the way. But in order to consider these environmental impacts, it's a very complex process. And this is a very hard problem because of its complexity. So we think some of these standards will ultimately help designers and manufacturers make better decisions throughout this whole chain of events that occurs here. So what's smart manufacturing mean for sustainability? It's going to help, like I said, help manufacturers improve their efficiency, reduce their waste, pinpoint opportunities for improvement to reduce their impacts. It's also going to help them virtualize their manufacturing processes so that they can simulate things ahead of time. They can look for areas, they can better understand the trade-offs they're making and look for opportunities for design improvements. And it will also help them optimize their processes and improve the transparency of where these impacts are coming from. And ultimately, to help them trace from strategic goals that they set for themselves to what needs to be done in the workplace to address those goals. So we feel that this road to sustainability is paved in standards. What, as a society, we'd like to do is be able to capture what the best practices are at any given time and then quickly deploy those in a widespread manner so that people can work to the best practices and be able to have some flexibility there so that we can improve those standards and deploy the best practices more quickly as we learn more about what we're going to do. And ultimately, though, when it comes to manufacturing or any type of enterprise, there are trade-offs that a business needs to make. But they should be able to understand those trade-offs, and by creating these standards, that will help them in that analysis. So standards to roll out our improvements. Bill's going to start with talking to you about a couple of ISO standards.
Thanks, Casey. So next we're going to go through a few standards that we find to be vital to kind of realize this sustainable manufacturing goal. Some of them we have lots of connection to, meaning that we've either helped edit or we sit on the committees for comments. Others we've just found through a literature search. So again, I'll highlight specifically the ones that we work on quite closely. So some standard groups that have focused on sustainable manufacturing have actually been around for quite some time. The first came to be the management standards, and this is really where the ISO 14000 group and the ISO 50000 energy management standards came through, and they've been around for quite some time. So mainly they focused on how you draft management procedures, draft reporting techniques, and things of that nature. Lately, there's been a lot of focus more on operationalizing some of these standards in a way that designers and manufacturers can leverage them in different contexts. So these are the three committees that we'll be focusing on in the next few slides. So the first one being ISO Technical Committee 39, which is focused on the design of machine tools. The second one being, which Casey is the vice chair of the subcommittee on sustainable manufacturing through ASTM International, and that will be very heavily focused in this talk since we have direct contribution in that community. And third, but not last, is the ISO Technical Community 184, which historically has been focused on traditional performance metrics for design. For instance, this is where the step exchange format for solid models came out of. But the SC5, the Special Committee 5, has a few working groups that are focused on energy or sustainable aware manufacturing standards. So we'll go through one of the efforts in that special committee. So like I mentioned before, these management standards have been around for quite some time. First of all, there was the environmental management, which basically gave a broad context to how you track the activities of an organization and what actually relates to the environment. The second one being very, very critical, especially for the people on this call and the community, actually formalizing some method for enumerating environmental impacts for products and systems. And thirdly being, there's the energy management standards as well. So in general, these standards had a very, very large impact. So as far as to say that even the life cycle assessment, there could be, for instance, some regulatory impacts in the United States. Clearly there have been in some in Europe. We argue that some organizations have kind of reached a saturation point where they might interact with third parties to develop these life cycle analyses, yet they might find some, so to speak, hitting a wall, and that they don't necessarily know how to leverage this knowledge for improving their own practices. So it's, again, our argument that manufacturers need to go a bit deeper into formally characterizing their manufacturing processes to continue finding the hotspots in these life cycle analyses, and then basically making improvements on the fly rather than developing new systems. So as a generality, here are some challenges that we see for life cycles, basically transferring life cycle assessment as is to better improve manufacturing from a sustainability perspective. One is there really is kind of a lack of improvement incentives for manufacturers. It's difficult since life cycle assessment kind of runs the gamut across the entire life cycle of a product. The manufacturer themselves has limited kind of power in effectively changing the total environmental impact of the product life cycle. So it's difficult to show specific means of improvement with respect to manufacturing. So at the point of when somebody's conducting a life cycle assessment, lots of the manufacturing process choices and how they're implemented are fixed. So the ability to kind of improve, the window and so to speak, kind of shrinks. And of course, they're using existing models that are in popular LCI data, lifecycle inventory databases is actually quite challenging for manufacturers, just because these models have been developed at a very abstract and aggregate level. We take, for instance, the sheet rolling unit process that you might find in, as an example, EcoVent database is very difficult to translate to finding specific improvements in machinery that maybe a sheet roller in Michigan is using, something like that. So this figure kind of generalizes and summarizes these challenges, that there are lots of existing parameterized manufacturing models in literature in these different databases that are either available through academic partnerships, or even the government themselves has some LCI relevant data. But to use these very specific models, it requires a good amount of expertise and cost to translate them to traditional LCA software. And what we've seen through literature is it's pretty much an academic exercise to develop tools to use these very highly specific manufacturing models. And it is through these red lines that you see in the middle of the screen that we hope that the standard, specifically ASTM E3012, which we'll dive into a little bit deeper, will really aid in helping people achieve these goals. So again, the left side of the figure and the right side of the figure are, we see it as completely kind of decoupled workflows, and we'd like to figure out ways to combine them. So now on to the four standards that we'll focus on, at least today. So there are many others. Actually, we've enumerated them in a slide. I think it's maybe the 5 or 6 slides down the road that you could go and check out on your own, and please ask us any questions after this webinar if you choose. So first we'll focus on ISO 14955. Then we'll look at ASTM E3012. That is the standard that our group is very heavily involved in. And we'll talk about ISO 20140, which I sit on the technical committee for, and another standard through ASTM International, to which our group is heavily involved, is linking key performance indicator selection for sustainable manufacturing. So a little background on the first standard that we'll go over, which is ISO 14955. So the idea of this standard is to influence the design of the machine tool itself. So they leverage existing frameworks from the 14040 series, like the original life cycle assessment framework, and they try to translate that into the eco-design phase and making prudent decisions for achieving a more sustainable machine tool. And the main idea here, as you see at the last bullet, they decompose this machine tool into functions to allocate the impact based off of that functional basis. So functions here is quite different than maybe some people think about functional unit. These functions are actual services which the machine tool provides. For instance, like you see these add-ons in the image matrix on the bottom left of this slide, where you'll have a coolant system which provides a certain kind of temperature to the cutting area. You might have a control system that provides some interface to the operator, and so on and so forth. Okay, and what they So what the end result of this kind of guideline for influencing the eco-design of a machine tool is you have this mapping. And on the left, you see these generalized machine functions. I described some of them in the last slide, for instance, like workpiece handling, different elements that achieve tool handling or changing the tool. And we link them to machine components, so the actual components themselves. And once you have this assignment and actually use subjective ratings to basically contribute how much each component is related to a certain function, you're then able to conduct an environmental analysis of these components and relate them back to the function. And this way you can kind of discover improvements for redesign. Okay, so there's a lot more to that standard. If you wish, you can ask us any questions later on. So the second thing we want to mention is our Special Committee on Sustainable Manufacturing through ASTM International E60, and these are some of the work items that are involved right now in E60.13. So E2986 is a standard that came out in 2015 that provides guidance for manufacturers to conduct a sustainability study, and this was kind of the preface to a much more kind of formal characterization of manufacturing processes in the second standard that came out, which is E3012. This came out in 2016, and it provides guidance for the deep characterization of manufacturing processes, for instance, with equations or different kinds of functions. We'll go through that in a bit. And of course, what's important through these standards and how they relate to one another is the terminology. So there's also a sister standard that enumerates different terms that are used across the E60 community, and we find that to be very important, especially when communicating these standards in practice with different companies. Like I mentioned before, we also helped move the standard through ASTM International on specifically gearing key performance indicators for environmental assessment of manufacturing processes. And there are two new work items, one of which is focused on waste or discarded materials from manufacturing facilities. I believe Amy Costello is the lead editor here, if you had any more questions. And then there's another new work item, which is from another division. The chief editor of this new work item is also at NIST in the economics division. So you actually saw some of his slides previously in this talk. So now we'll focus on a standard that we're very excited about, which is E3012, which proposes a formal characterization of models. And we see this really benefiting the main challenge that I presented earlier in relating higher fidelity models to life cycle inventory analysis. So like I said, the intended goals is to formally characterize manufacturing processes. It also can be used as a communication tool in which we are trying to capture or link to different aspects of the manufacturing facility and how they influence the environment. And hopefully, if it's implemented correctly, we'll be able to support composition of these models for higher level analysis. And the target users, in our minds, are mostly people that plan out these facilities, want to improve the facilities, or are designing products. So one of the core components of the standard is this graphical representation, which is meant as a communication tool in enumerating all of the different linked information that's relevant for fully understanding a manufacturing process. And just to be clear, what we mean by input here are actual physical inputs into the process, meaning like electricity or material. And when we say output, we mean physical outputs to the process. Could be waste, could be the product itself, could be any byproducts, especially, for instance, in a chemical process where byproducts are very valuable. And on the bottom, you see we track resources, so physical resources in the shop floor that have relevance. For instance, you would list any of your equipment that are used for the build. And on the top, the idea is to link to product and process specific information, whether they're material data sheets or CAD file, computer-aided design files, solid models, things of that nature. So we'll just go through an example of how you could use the standard. And actually, this is a use case from a competition that we ran. We actually elicited mainly academic researchers to use the standard to formally characterize models that they have been developing over their careers. One of which, on the right, you see is an atomic layer deposition process model, which is relevant for semiconductor manufacturing. And the idea of formally characterizing this, again, is to communicate what the model entails, what it is, and if it's operationalized, you'll be used to calibrate the model so that you can maybe optimize the best controls of this process. And again, another main use case here that we see as a benefit is to actually generate life cycle inventory data based off of different conditions that are seen on the floor. So on the right, and sorry, we know that this is quite small, so it's not really intended to read, but on the right, basically the model that was developed to describe the atomic layer deposition process is shown here in the graphical representation. So in the middle box, you see all the relevant equations that relate, equations and transformation functions that relate the inputs and product information to the outputs. So in this case, it has some chemical balance equations, but then also has, for instance, like more engineering-focused procedures, for instance, like the Naves-Stokes momentum conservation equation. And what we're very excited about is not only is it used as a communication tool, we also have recently proposed a schema to be able to track and store this information in a XML schema. So on the left, we're just showing it's not the whole model. This is just a depiction of the components of this unit manufacturing process model. Next, we'll just mention some work going on in ISO, specifically in the TC184 SC5. So the first one we're going to more focus on, which is a standard relating to evaluating energy efficiency and other environmental influences of manufacturing system. And of course, there's another working group that's focused on bringing more sustainability relevant key performance indicators to an existing standard that my understanding is highly disseminated, which is 22400. So the idea of 20140 is primarily to classify different sources of data that are relevant for assessing the environmental performance of the manufacturing systems. So they have this idea of indirect influence, which you can think of maybe as HVAC systems and other auxiliary systems, not specifically directly related to the process. And then they also have this way of classifying different kinds of environmental influences of direct influences, which would be, for instance, the material, the energy needed, the cutting speed of a machine tool, things of that nature. And the idea is that once you understand where all these data reside, you can in a better manner develop a scheme for understanding the performance of a manufacturing system. So it's used to benchmark manufacturing systems and also improve. So the two standards that we kind of dive a little bit more deeply into, which is 3012, the ones that we're highly integrated in, and then also 20140 are very similar to one another, and we find that to be a good thing. So hopefully there's some harmonization and alignment opportunities in the future. We're just now starting some early talks on how we can use this data classification of influences that 20140 leverages, and how that would improve the modeling capability of our E301216. So this table just shows some differences and similarities between the two. So it's a nice summary of the two standards. So 301216 again is focused on modeling, and once things are modeled in a consistent manner, would aid the curation of those models, and also with the graphical representation helps in the communication of what actually is being modeled. 20140 is more about monitoring the process through this data classification, allocating impacts based on where exactly they're coming from. For instance, whether your let's say your energy influence is more handled by the HVAC system relative to the actual machine tool, and assessing based on benchmarking. And you can, after this talk, feel free to read more on this this slide. So this is just and we see at the top, we show the way that we see how these two standards are used in kind of the manufacturing life cycle. We think of designing manufacturing systems, then planning out builds, tracking the execution, and so on. We see that ASTM E301216 is a little bit more relevant on the upstream activities of this life cycle, while ISO 20140 can be helpful in the planning and actual execution of part builds. So with that, I'll hand it off to Casey. She'll talk about the KPI standards.
Okay. The most recent standard that we NIST have been very involved in within ASTM E60 is on KPI related standards. And it's, well, okay, sorry, take a step back there. A KPI is a quantifiable level of achieving a critical objective, and there's actually a number of different standards that deal with KPIs. So this slide is going to give you a little bit of insight into what those are. So the first standard that the E60.13 committee and ASTM produced on 2986 calls for the definition of KPIs. That standard is for helping people evaluate their manufacturing processes for environmental improvements, and KPIs are critical to achieving that. 3012 also directly calls for KPIs specific to the different processes that it's capturing, that it's used to capture. ISO 22400, which Bill mentioned briefly, is a standard for MOM level, manufacturing operations management level KPIs, and that standard has been used to formally define what a KPI should look like, and we'll get to that in a second. And then, as he mentioned, there's an amendment to that standard to look even more specifically at KPIs for energy management. Now, that is work in progress, and that standard is not available yet. And then finally, this standard that I'm about to talk about, it is the one standard that talks about how do you go about developing a KPIs. The other standards reference them and use them as opportunities for improvement, but 3096 actually talks about how you use it. So I'll go a little more deeply into that in a minute. First, this was not intended just to test your eyes, which it's doing to mine. But this is the standard format for representing KPIs that's defined in 22400, and we've reused that again in the ASTM standard. So in the ASTM standard provides guidelines for a manufacturer to use to define KPIs. It's not it does not include KPIs themselves, although it does provide some references to sources of material that do define KPIs for people to look at. But the idea here is that in any given specific instance or manufacturing enterprise, the people involved in that are going to be the ones that are able to best decide how they can improve their systems. And so this gives them guidelines on a systematic way to go through doing those definitions to select the best KPIs for their own objectives. So there's 5 steps involved. The first step is to define what the objective is, identify candidate KPIs, and that's where the references to different sources come in. Though they're not exclusive, but there is a number of references there that people can look at. The next step is then to define the new KPIs, either drawing from already defined KPIs or creating their own when those are necessary. And then evaluating the effectiveness of the KPIs against your own value sets, and I'll go into that in a little more deeply. And then finally, once you've done that, you can identify a final set of KPIs and organize those into the sets that you'll use for your evaluation. So what do we mean by effectiveness? I've drawn from this report from the National Research Academy to kind of illustrate this. Back in, this was in 1999, they surveyed manufacturers and asked them what made an effective KPI. And the top 2 that come up here are that they're comparable over time and that they're verifiable. And so those are very good criteria. There's a number of others listed there, but that's what we mean by effective. What is it going to be effective in your environment? Is this something that's going to help you? So guidelines on effectiveness in this document, in this standard, get a little more detailed. They tell you to determine what criteria are important to your stakeholders before you start evaluating the KPIs. So the idea is to take a step back and think about what are those things like verifiable or standard or constant over time. Are those important in your environment? And so I let people take a step back and reflect on that and decide what the values are that they hold that will apply to these KPIs. And then once you've decided on what these are, then you go through your stakeholders, and it's important to bring in stakeholders with different viewpoints to then rank the KPIs as to whether they meet those criteria. And then once you've come up with a ranking of the KPIs, you can select a cutoff, and the ones that percolate to the top are the set of KPIs that you'll use. But what's important in the standard is that you do get viewpoints from multiple different stakeholders to address this. So, so those were the standards we were going to go through. I'm going to tell you a little bit more about what we're doing here at NIST to further this research, because standards are one piece of the puzzle, but you can't have standards until you kind of decided that this is the right way to go. So we're involved in a number of different activities. The one that I want to mention here is called the UMP Repository. UMP, I don't think we defined here, but when we talk about characterizing manufacturing processes, Bill showed you the graphical form. We call that a unit manufacturing process model. And so the UMP repository, the idea of that is that we're able to collect a lot of these different models covering many different manufacturing processes into a single location that people can then go to discover models as they're trying to plan their next set of manufacturing systems, or want to study a particular process more deeply. They'll have a reference model they can use as a basis for that study. The idea is that we'll be able to pull together collective community knowledge about the different processes. If you've ever tried to learn about manufacturing processes a little more deeply and you do a literature review, you'll find that many processes have been studied from many different angles. But one thing that is lacking is a consistent representation of those studies. And so the ASTM 3012 provides that consistent representation, which will help people manage to find the information they need more quickly and to make use of that more quickly. And presumably it would also help the people preparing these studies to make sure that they're covering all of the different aspects that they should. So this repository, in our view, this is still a future vision, but as you'll see in a moment, we're taking some steps along that way. But in our vision is that it would be a collection of different process models that would be peer-reviewed in some way. It would provide that reference data for people wanting to study different processes, and it could be a showcase for research as researchers produce more models. If they produce it in the format, we could include it into this repository. So in that direction, last summer we hosted a competition on reusable abstractions for manufacturing processes. That's what we're calling it, RAMP. And that was our first effort to get the community more aware of the 3012 standard and to use it and apply it to manufacturing processes that they've defined. And we'll be repeating that competition. We are repeating that competition this year. In June, it will be held again at the Manufacturing Science and Engineering Conference. And this is the website to go to. The official rules for this year are not up there yet, but they will be up there shortly. So just to say a little bit more about this repository, the idea is that people would model manufacturing processes, their own work or publications would be sources of those processes, model them in the 3012 standard, submit them to a repository that could then be peer-reviewed, and the models themselves should be validated through their own research, and then that repository would then be available to the public at large, and there would be ontologies and taxonomies that would help people find what they were looking for in the repository, and by doing that, by providing them in this formal way, that could be integrated into external tools as reference models for those tools. So after the competition we had this year, we also had a workshop with the research community who attempted to use the 3012 standard and presented this idea of a repository of these models, and we developed this research roadmap, it's not exactly a roadmap, it's more like a sphere of challenges for the research communities to start to address to make that vision a reality. So the things you see in the inner circles there, that's research that is relatively mature, that we feel could be a strong basis for building out this repository. As you move out to the outer circles, these are challenges that still need to be addressed to make this concept even richer. And that's the end of our presentation. Thank you for listening. I hope you all learned something, and we would love to have some questions.
Great. Thank you, Casey and Bill. That was really fascinating. We actually do have quite a few questions, and I want to encourage anybody to keep sending me questions through the private chat if you would like. So we had a bunch of questions actually about application of the standards. I think we'll start there. And the first is Casey, can you share some specific examples, real-world type examples, of smart manufacturing and the standards in the wild?
Well, smart manufacturing and standards in the wild, that's a big, thing. So smart manufacturing, there's many examples of that. As far as the use of these standards, they're relatively new. We're working right now with Armstrong Armstrong Flooring, who also participates in the ASTM E60.13 committee, to apply those in one of their factories where they're having a problem with waste. But other than that, no, I take that back. Okay, so it's also, the 3012 standard has also been applied in the pulp and paper industry. to look at how to improve their flows. They were actually using the UMP modeling composition to understand where their wastes were coming in terms of the transportation within a quarry where that was. I'm sorry, that's a rock quarry. There's also pulp and paper study. Yeah, so that's a short answer to your question.
Okay, well, we actually have a really good follow-on to that, and that's what sort of timeline then do you envision for adoption and implementation of standards like these?
Well, that's a very good question. I would hope, I mean, we've been trying to make the community more aware of these standards. The standards are out, you know, in the last 2 years, really. I do not have a good answer for that. Unfortunately, NIST is a research lab, and we do not have really a marketing arm. I hope that they will be picked up in the next couple of years, 2, 3, 4, 5 years. Through the competition that we're sponsoring, we're trying to get them included into curriculum in the engineering schools, and that is succeeding to a certain extent. We are trying to arrange a workshop on curriculum development to make that even more the case. So I think as people become more and more aware of them, especially through the students, the next generation of engineers, they'll get more uptake. But that's the best answer I can give you.
So of course this is still in kind of a research phase, but we've pushed towards developing toolkits that will hopefully be hosted externally for people, basically to lessen the barrier of entry to these standards. So an example of one of those toolkits, which is in production right now, so it's still very early, basically creates a form, an online form that someone would fill in, and it would automatically inject it into the ASTM 301216 schema. But again, that is a very early research. We have a working prototype, so I can envision that these kinds of toolkits will at least quicken the adoption of the standards.
Yeah, and there's another toolkit as well on the KPI standard. Our partners at Old Dominion University have built a toolkit around that, and that's available through their website. So as these tools become available, I think there's a lot of opportunity there for people to start using them, and it would be wonderful if there's any small tool developers that are commercial enterprises that want to talk to us. We would love to talk to them, because I think there's a good basis here for tools to be developed on.
Okay. Is there any sort of framework to support that kind of collaboration?
Framework. Well, there's possibilities. There's the small business, SBIR programs available right now. I think that's the new competition hasn't come out yet. There's also possibility for collaborative research with NIST. Yeah.
Great, thanks. So these are fairly detailed and complex things. Bill, could you take one of the standards, just pick one, and walk us through how the standard would be applied and maybe what kind of results we might expect?
Sure. So actually, let me just, sorry for cycling back. So I wish I had, okay. So if we use the ASTM 301216 as an example, so like I said before, what we're focusing on right now is augmenting the schema, so the back-end information representation of a model, of a manufacturing process model. And what that can do, and we've demonstrated through some kind of simplified use cases, is we can basically store operationalized code, and you can think of it maybe as Python scripts. In our case, we've implemented it in a language called JSONic, which is a query language for JSON representations. And basically, you can think of it as exploring the space of a model by changing the controls and parameters of that process. So I'll give you a simple example. If you want to machine a part, as an example, there are different controls or knobs that you can tune on the machine to get different outputs. And some of those controls would be the spindle speed of a tool, so how fast it's rotating, feed rate of the tool, how fast it's kind of shaving the material, and depth of cut, the distance that it's engaging in the material. And all of those three variables greatly influence the energy consumption of the machine tool. So right now we have a model that we've demonstrated that that calculates or evaluates the energy consumption based on these different control parameters. And the idea is that when you have these relationships formally modeled, you can then optimize these control parameters to whatever outcome that you're interested in. For instance, if you have a let's say that you have a ceiling for how much CO2 emissions you're looking or you can withstand, then you can optimize the controls to stay within that as a constraint, but then also maybe minimize cost staying within that constraint bound. Did that help?
Yeah, I think that was a very informative response. Thanks, Bill. So we also had a set of questions kind of about the development process as a whole, and one of the big ones is who developed these standards? Can you guys comment a little bit on whose voices are really heard in these?
Sure. Well, all of the ISO standards and the ASTM standards, of course, are open standards. So they're a community-based process. In the case of the ASTM standards, NIST has been very heavily involved, and we're leading some of the authorship of some of those standards. But then they are reviewed by the membership of the ASTM E60.13 committee, and then the E60 committee, which is the parent of that subcommittee. So a lot of those people are from the building industry. They make products for construction like gypsum board and piping and a whole variety of the things that go into construction products. But anybody is welcome there, and there are definitely other organizations represented. And there are also consultants that participate in these standards committees as well, because they can use this work in their consulting practices to take to businesses as a good practice to follow. Within ISO, it's more of an international community, although ASTM is international, and there are some international participants, but it's heavily dominated by the U.S. Within ISO, it's more broadly international, and the standard that Bill talked about has been brought forward by Japan. So they've been the ones promoting that, and we are participants, so we're among the people who review it. Anybody, I think it's open to anybody in the U.S. really to review as these standards come out and, you know, make comment on. Yeah, so those are the two standards that we covered here.
Okay, great, thanks. And we also have some questions on one of our favorite topics, on LCA. So let's start with those. You guys touched on a major issue, and that's data or the lack thereof. The biggest challenge we see in LCA in manufacturing is that companies don't have the data at the granularity needed to model the process. Specifically, they don't have the process-specific energy. Does this help address that? Are there gaps in rolling things out? You want to comment on that?
Okay. So there's multiple ways to address that question, and it's certainly in the development stages. So I'll take I guess, two-pronged approach. So first, if 20140, the standard that we mentioned about classifying different influences of data across the factory floor, let's say that was disseminated and accepted throughout industry, it would at first kind of, I would think, kind of encourage people to use consistent tools across supply chains, and it would be easier to even start with communicating what kind of data we need to collect. So that I think needs to be done because people are in terms of even terminology and jargon, use very different language in describing how their processes are implemented. Okay, so secondly, we didn't really touch on the progress of more, I don't know if traditional is not the right word, but other very influencing smart manufacturing standards. For instance, like like MT Connect is one standard that we didn't really mention, which is a way of basically capturing points in time and what's happening on the manufacturing floor. So it actually streams data in a time-stamped fashion back to in a parsable XML document. And of course, there's still a lot of research needed. But if we can better understand how machine tools behave in real time using tools or standards like MT Connect and relating that back to, for instance, traditional unit processes like you can get in Gabi databases or EcoInvent databases, you would at least, I would think, restrict the uncertainty space to something more manageable. So at this point, I agree with the question that, or the person that posed the question, that the kinds of data that's required in order to conduct hotspot identification in these complex production lines is simply just not there. But I think that democratizing these kinds of technologies, for instance, like MT Connect agents that stream information, will at least invite more people through the door.
Okay, that sounds great. And I think we're rapidly running out of time. So I think I'll leave us with one last set of questions, which are, I suppose, how can we participate in the standards development process, and how can people participate in the competition?
Well, ASTM is, you can join ASTM. It's a $75 membership, and then once you've joined ASTM, you can be a participant, a member of any of the working committees, including ASTM E60.13. So we'd love to have people join there. ISO is a little bit higher cost entry. I don't remember the specifics of that, but it's certainly an open process, and I believe people typically have an organizational membership in ISO versus the independent individual memberships in ASTM. And the RAMP competition, I think we did include the website there. Do you remember off the top of your head the name of the website? It's challenges.gov. If you go to challenges.gov and search RAMP, it is the website for the competition, and the rules will be being posted there in the very near future. The deadline for entries is going to be, I believe, sometime in March, and that will be posted there once those are available. What you'll see there right now are the rules from the competition for the previous year. They're very similar set of rules. This year we have a theme focusing more on the system level composition of these models. But it's a similar set of rules, and you can see an example in the webinar we put together last year about the competition to see kind of what it's all about.
Great. Thank you very much. And thank you both, Casey and Bill, for a very informative presentation. This concludes our last webinar of the fall season. We'll hope to see you all in January on the 25th when we kick off with Chris Wigal from the Resonate Materials Group and start talking about plastics. So thank you all very much. See you next time.
Thank you.